Off करने दे.
Hello, Solomon.
Hi. I can hear you.
Please, those who are hosts, please kindly be checking if there's noise at anyone's background so you can mute them as well.
All right. Okay, hi everyone. My name is GCRC. I am the organizer for GCRC, that's Ghana CanSat and Rocketry Championship. And I'd like to welcome everyone to this design CanSat workshop. We have two guests and we'll introduce them shortly. But before we do, I would like my co-host Jemima to tell us a bit about what the Ghana CanSat and Rocketry Championship is and what the World CanSat and Rocketry Championship entails. Jemima.
Hello, Jake. Thank you very much for the introduction. Can you hear me?
Yes, we can.
Okay, all right. So we, on behalf of the GCRC and the VCRC team, warmly welcome you to this workshop. The events and workshops are important for the competition's participants. However, they are open to all who want to learn the things discussed here. For more information on the competition, including how to join us and be a sponsor, kindly email us at cansatghana@gmail.com. Once again, cansatghana@gmail.com. All the relevant links and information you need will put in the chat right after my presentation. The Ghana CanSat Rocketry Championship, GCRC, competition set up by the Committee for Space Program Development, CSPD, and under the World CanSat Rocketry Championship, WCRC, which is an organization in Serbia with collaboration in Europe, Africa, and other continents. The World CanSat Rocketry Championship is generally an international competition open to elite competitors from all around the world, representing their nations as student teams or as independent participants. GCRC is being led by Xavier Space Solutions, a space setup in Ghana founded in 2019 with a single mission: to help space enthusiasts and students to get access to services and logistics that will make exploring the universe easy and enjoyable. XSS is working in partnership with the Space Generation Advisory Council, SGAC Ghana, on this competition. GCRC is sponsored by Academic City University College, X Space Solutions, and most recently, Electronics. GCRC is also supported by the World CanSat Rocketry Championship and Committee for Space Program Development, among some other international partners. World CanSat Rocketry Championship, India, etc. Winning this event will be considered the highest or near highest achievement in the field of space science, education, and awareness. This event is the first ever happen in Ghana, setting the pace for space science technology awareness in the country. The only countries in Africa with satellite launch sites with WCRC are Morocco and South Africa. However, due to the launch of the competition, Ghana will soon join that list. This launch happened at 31st July 2021 at Academic City Campus. Students from all over Ghana, Africa, and the world attended the hybrid event and had knowledge and motivation impacted to them by many key players in space science and technology in Africa, and dare I say the world. This was not only the first ever satellite design and build competition in Ghana, but also a wave of space science technology awareness in Africa. The competition is based on designing a CanSat. A CanSat is a simulation of a real satellite integrated within the volume and shape of a soft drinks can. The challenge of students is to fit all the major subsystems found in a satellite, such as power, sensors, and communication system, into this minimal volume. The CanSat is then launched by a rocket or drop captive balloon. Then its mission begins. This involves carrying out a scientific experiment, achieving a safe landing, and analyzing the data collected. That we organized was on how one will engage in 3D modeling the concepts. We are currently organizing the second workshop to learn about the electronics needed. Last year, we had a wonderful and successful workshop on introduction to electronics. And this, what we are having right now, is the second chapter of that workshop, to Arduino systems. For those unable to attend that workshop, you can access this on YouTube. The YouTube link is CanSat Ghana. I will link all the links into the chat. This is a 3-day power-packed and high. First day, that is today, will be on the hardware of Arduino systems. The second day, which is tomorrow, will be on the software necessary for the Arduino. And the third day, on Wednesday, will be on integrating the software into hardware to do amazing things. Now, the workshop has officially begun. I would like to invite my partner, Jake, to take over the introduction. And once again, everyone, you are all warmly welcome. Thank you.
Thank you, Jemima. So we'll just begin the workshop. I'll introduce our first speaker. So our first speaker will be talking on designing CanSat, that is on the software and hardware aspects of CanSat. So I think he'll give his rules, but if you have any questions, you can ask after his presentation. He's the chief engineer and also the chief engineering officer and also the co-founder of TSC Technologies Private Limited in India. He's also the organizing head of the South Asia Pacific for the World CanSat and Rocketry Championship. Mr. Ashwin Reddy, you're welcome.
Thank you, Jake, for that beautiful introduction. Let me just quickly share my screen.
All right.
So you're able to see my screen? Okay, perfect. So good evening, guys. Like just mentioned, I'm here to talk about about a CanSat, and mostly I'll be covering a brief introduction about how things are assembled, built, and also the sequence and how the entire event takes place, and also about some design that we have followed in the past. There are multiple kinds of designs that one can follow, and there's no hard and fast rule as to how a CanSat is supposed to be built. So I've picked a particular design that I've designed earlier. So let's get started. So just to give you guys an overview, these are the things that I'll be talking about what a CanSat is and what is the abstract of the entire presentation, along with the subsystems that the CanSat consists about. It could be all the different systems that are put together as one to realize an entire CanSat as a whole, and what are their uses and what is the role of each subsystem, and about some software description that we have used. Of course, I'm not going to go much in detail about how these softwares are used, or how everything is designed in these softwares, but I will give you a brief about what software is used for what reasons, and and how everything can be gotten to with those particular systems, and about how this entire CanSat works as a whole. Apart from building, designing, and building these, the most important part is integration. So only if all of these subsystems are integrated in the right fashion is when we'll be able to realize a completely working or a fully functional CanSat. So that being said, we'll then look at some kind of testing, which is a key factor. Only when you test things is when we figure out how things can be improved, or if there are any issues, how they can be corrected, and such things. So that being said, it's not just enough for us to build CanSats. Of course, CanSats are a stepping stone, and we need to take this as a preliminary or a primary step to build to move on to building CanSats. I mean, CubeSats and bigger satellites in the future. So that, of course, will be covered in future enhancements, and also about how CanSats can be improved further. So to give you all an abstract, the reason why we have come up with these CanSats. To start with some basic history, back in the 90s, when the CubeSat revolution started in California Polytechnic. Uh, it was basically to revolutionize the space industry. So what was being able to done by huge geostationary satellites, or satellites in the size of a small car, or about satellites weighing hundreds of kilos, can now be done with satellites weighing less than 3 kgs, and with with the help of constellation of these small satellites, we can we're able to achieve such humongous or enormous tasks that we'd once require extremely large satellites to do. So when you look at the advantage here, about what is the advantage of us, coming down with size? Why are we troubling ourselves by giving us less space and not having bigger space to work with? So there are quite a few benefits, and one of the main reasons I see here is, let's say you launch about 100 satellites instead of one single satellite. So any small component, or let's say even like very small component that fails in a satellite, it could result in the entire mission to be a failure. So it could be the batteries, it could be some kind of the thermal or heat system, it could be anything. Any one single point failure can ruin the mission completely. But in the case of CubeSats or smaller nano satellites, when you, let's say you're launching 100 of them for the same mission, and even 10% of it fails, you still have 90 satellites available for yourself. I think there is feedback. Okay, this sounds good. So when you think of that, 10% of your mission fails and you still have 90 satellites to go with, isn't it great? Like you once we have spent a lot of time, energy, and most importantly money on these satellites, and we have a failure, it doesn't ruin the mission, it doesn't put all our work in drain, right? So this is something what we call as failure optimization. And not just that, to launch these really huge satellites, we would need bigger rockets and more sophisticated orbits, like putting these satellites into a higher orbit, or even in fact with respect to launch costs, it's more expensive to launch bigger satellites, of course. So if you look at it from an overall perspective, miniaturization of these satellites from big to small has resulted in many advantages. So that is how these cube satellites came into picture, and the advantages were seen. And now now that we have cube satellites, how does one start getting into CubeSats? How does one start designing CubeSats? Isn't it difficult for someone to just randomly get into satellite building and put in a lot of time, effort, and most importantly money, and not being sure of whether it will succeed or not, right? So so that point is where we come up with this entire concept of a CanSat, which is nothing but a real simulation of a real satellite. And that's where we build something exactly like a satellite, but only that it does not have go into space. It's far cheaper. And but we always get the entire experience of building a real satellite. So that is the real motive behind working with CanSats. So just to mention about some literature surveys, so these are some documentations that you could refer and read about CanSats in more in detail if necessary. So to get into the topic, what is a CanSat? So how does one know what really is a CanSat? So going by the definition, a CanSat is nothing but a simulation of a real satellite that's put into a size of a Coke can. So it, of course, it has design constraints which says the diameter should be 66 millimeters and the height nothing more than 115 millimeters. So that size being the size of a Coke can, it's a task or a challenge that one generally takes up to put all the systems and subsystems that we find in a real satellite into the CanSat. So, like I said, this being the stepping stone or like the preliminary step, we get exposure to different kinds of subsystems from what we see in the further slides. So everything that goes into building a real satellite, a smaller or an easier version of it is goes into building a CanSat. So once we achieve building this CanSat, we can be sure that okay, now that I know how this works, I have a fair understanding of all the technicalities that are included in building a satellite or a CanSat. So can now be put to building real satellites. Of course, would need more data, more information, and that we can learn as we go ahead. So that's something about it. And like I said, the difference between CanSats and CubeSats or any other satellites is that these CanSats are not put into orbit. Rather, they're launched to what is called the near space uh, area where these CanSats are launched up to almost 2 kilometers in height, depending on the kind of rockets or drones or any kind of launch mechanism that we use. And once these CanSats are put into some altitude, and during the descent is when the CanSat is actually functional, and it picks up readings or values that one wants to use and measure. So moving ahead, we can look at what the subsystems or what this CanSat consists of. So to talk about every subsystem, to give you a comparison, CanSats or any satellite for that matter is not very different from a human body. So when you think about a human or the general body structure, one has brain, one has some nerves sending signals from one part of it to another. One has an entire system for energy and about what we generally do. So things like these, right? So in this case, the onboard computer is nothing but the brain of the CanSat. So it houses a microcontroller, and it's responsible for the command and data handling, which is it takes in information from all the other subsystems and coordinates between different subsystems to work together in sync, so that targets are achieved, and what the entire system has to be doing at one particular time is maintained in sequence. So this this being one of the important subsystems is responsible to make sure that all of these components have no particular issue to coordinate with each other also. So apart from that, when you say electrical power system, it's something that gives power or an energy to the entire system. So we have the brain, but without electricity, or rather any kind of power source, of course it's not going to work. And when you say you have a communication system, even without power, of course even that's not going to work. So this power system is also a very crucial subsystem that's housed in a satellite or a CanSat, and it makes sure that all the power is either drawn from a battery, or some cases solar cells also, and that power is like brought into the system and then distributed to other subsystems like onboard computer, communication system, payloads, etc. So that's generally about what an EPS is. So moving ahead, like we do all of these CanSats and everything. Fine. We have multiple payloads on the CanSats. Okay. But what's the use of this if a CanSat does not have a communication subsystem? Let's say you have a very sophisticated CanSat, you launch it into atmosphere, or you launch it into near space, and it takes in all the readings. It functions perfectly fine. But let's say if you're not able to get the readings to the ground station, so what is it serving? What purpose is it serving? Same with satellites as well, right? Once you launch them into space, there's no particular way of you recovering the satellite. So all it has to do is send information from space, be it position data, be it some kind of pictures that it has clicked, or any kind of information that a satellite is collecting. If it does not send it to the ground, there's absolutely no point of it being there. So communication module is again one of the very important or a key subsystem for us to have in a CanSat. And so this same module can be split into two parts. So one is something that is on the CanSat or the satellite itself, and the other half of it being at the ground for us to receive, and also sometimes send data, or rather not data but commands to the satellite. So that is what excuse me. So that is what a communication subsystem is. And a payload, coming to payload. So when you think of any spacecraft, all of these subsystems are there for the functioning of the satellite itself, right? But what is the use of us launching a satellite? What does the satellite do? How does it matter to us if a satellite is in space or not, depending on what work it is doing, right? So how is it beneficial for us to launch a satellite? By the amount of data that it's going to give us, and we are going to work and study on that data and use it for our day-to-day lives. So with this in mind, if we need images of the Earth, or let's say we need to study the magnetosphere of the Earth, then we have particular sensors for that. So if we need images, of course, we have cameras that are inbuilt in the satellite. So these or these sensors or any kind of devices or components or instruments that are fit in the satellite or a CanSat that gives the CanSat a meaning or a purpose is what is called a payload. To give you an example, at least in this particular CanSat that I'm showing you, these have been embedded with weather sensors, temperature sensors, and pressure sensors. So as the CanSat is launched at an altitude and during its descent, so it measures these atmospheric parameters and values to give us data back down to ground. So this is what gives the CanSat or the mission a value and a meaning. So these are typically the most important subsystems that are present in a CanSat and of course a satellite too. So to go slightly more in detail about what these subsystems consist. So I have listed down some specifications that we could look at. I'm sure in the further sessions you'll be covering about how an Arduino can be used for CanSats. So this is nothing different. We, of course, even we too have put together Arduinos into CanSat and build them. But the only difference is that we have at least here I have not integrated the entire Arduino card as a whole. Rather, we've extracted only the microcontroller and embedded it onto a custom designed PCB. Of course, it's not mandatory to do such designs. One can design with the boards. One can design this way, and of course, people can come up with multiple other ways. There is no hard and fast rule as to how a CanSat should be designed. It's up to you guys. It's up to how you want imagine it and how you want to be. So there is no limitation to the way you can think or the way you can you want your system to look like. So that being said, of course, the microprocessor is the Atmega 328P and operates at 20 megahertz. So this is an important feature where we should keep in mind about the operating temperature. So it goes from -40 to 105 degrees Celsius. And these components are generally referred to as COTS components, commercially off-the-shelf components. So the good part about these are this can not only be used on CanSats but also on CubeSats. So generally, once they're in the satellite, they have -40 to 105 is a good enough temperature range to be embedded into satellite. So that is something that people generally do too. And of course, it has a 32 KB flash memory. For a CanSat, I think that is more than sufficient. And the interfaces that is used for connecting the microcontroller along with other subsystems and systems or SPI and serial UART and things like that. So moving ahead, just quickly, we can discuss about how these communication protocols work. So you see these leads here, these black leads around the CanSat. So these work as headers, and that is what connects one system to another. And it's all the communication interfaces have been connected to these black headers, so that there is a link between each subsystem. So coming to electronic power system, of course, it's a very simple design, and we have done the same as to instead of using a ready board, just to make it more challenging and fun, we have tried to design it by ourselves and extracted components and ordered components, and designed it on this custom design board. And of course it has buck boost converters, and most of these operate at either 3.3 or 5 volts. And we have a short circuit cutoff as well, which means just in case there is a short, the entire the power gets cut off, and that is a safety feature. So with this, sometimes there could be a requirement for our payloads, any kind of payload, that we would need certain amount of current to drive the payload. So for that reason, we have a 2 amps current for each of these rails. And again, these temperature tolerances are pots, so they are -40 to 125. That's absolutely perfect. We don't need more than this. Actually, this is more than sufficient for us to have components like these on CanSat. This is it is something that anyone could ask for at the most. And moving ahead, a communication system, like I said, is what would one do without being able to communicate with your system? So that kind of amputates people if we are not able to communicate to the system. And hence we have used a LoRa based communication system, which is very simple to integrate and work with. And has like I said, has 2 parts to it. One is a telemetry and one is a telecommand. As to what does a telemetry and telecommand mean? So when the CanSat is up in the air, and all the information that it sends to the ground is called telemetry, and any kind of command or operation that we ask the CanSat to perform from ground is called telecommand. So ground to satellite or ground to CanSat is telecommand, and satellite to ground is telemetry. So this can be done in either half or full duplex configurations, meaning half as in either telecommand at once and telemetry at once, or both at the same time. So depending on of course the antennas come in this particular subsystem. Antennas are a part of this particular subsystem. Designing the antennas largely depends on what frequency you choose for these, and generally people choose frequencies that are open to the public, and that varies depending on the country to country. The frequency range that one can operate in varies. So based on what frequency is permitted, you could just choose a frequency and try and communicate. And also the length of the antenna depend on the frequency we have chosen. So higher the frequency, lower the size of the antenna. So we should also make sure that the antenna fits in the CanSat structure. Excuse me. Yeah. So we should also make sure that the antennas fit in the CanSat structure. So we have to be slightly careful when we choose the frequency. So sensor boards, I've already told you what they are and why they are there. So here we have used 9SS IMU, which has an accelerometer, gyroscope, and a magnetometer. So it can give us values based on what is the angle that the CanSat is spinning in, and about how fast CanSat is descending down, and also of course the magnetic readings at that particular point. So apart from that, humidity, pressure, temperature, and VOC, which is volatile organic compound. So these are just some chemical values that are present in the atmosphere. So basically, as a whole, if you look at it, these are atmospheric sensors that read values from the atmosphere itself. So like I said earlier, all these sensors are connected to the onboard computer. So the sensors generally sense all of these parameters, convert them into electrical signals, and send them to an onboard computer. And the onboard computer processes, this information and then sends it to a communication module, and the communication module is then sending all the data back to ground. So that's something that happens as a sequence. So I've just included a slide from the communication subsystems about some basic values about sensitivity, the range, power consumption, and battery replacement cost. So we have good sensitivity level, and the range of 30 miles I think is really good for a CanSat. Power consumption is low, and that's why it's called one of the reasons it's called LoRa is because the power consumed is low. And as not having solar cells or anything of that sort, just relying with small batteries, I think it's good to have elements which consume less power. And not just that, it's very important for any designer to design the system very in an optimized manner, so that your systems don't consume a lot of power. So that's one of the key things that a designer should keep in mind. So of course, once you use these batteries often, it should be such that you don't have to always get a new battery and things like that. So that being said, we can now move to the softwares that we've been have been used to build these CanSats. So one of them, let me start with extremely important software, at least that we've used, are let's say EagleCAD. So at least in this particular design, we have designed all the boards by ourselves, and that we've done using EagleCAD. And EagleCAD is now embedded into Fusion 360, which is a 3D modeling software by Autodesk. So here in Fusion 360, we've used it to design the structure of the entire CanSat itself, and also the 3D models of all the CanSat that you just saw was also designed in Fusion 360. So apart from that, Arduino IDE, I think, is an extremely important software, because without Arduino, like, you wouldn't be able to port the CanSat, and you wouldn't be able to get the CanSat running. So that's something that we've used to put all of these together. And the other ones are just to make things more better, and also it's just about more like a presentation part of it, to get things better, like have a GUI for the ground station part of it, where instead of just having raw values, some a representation like a meter or altitude meter, or representation where the height it has gone, some graphs and things like that. So to give some light on the workflow of what a CanSat is during action, is that it starts with initializing the system and resetting the values. Of course, once the CanSat is assembled, we have to reset the CanSat and make sure it's on, and put it into or load it into a rocket or a drone or a balloon or any launching mechanism. So once that's done, it's launched to a particular altitude. And we should also make sure that the battery is sufficiently charged, and also about how fast the discharge is happening and things like that. So once these CanSats are at an altitude, and when they're deployed, or when once the CanSats are released into air, so it's since then that the CanSat or the mission of the CanSat begins. So the parachute opens, and during its descent, it reads values, or it does any kind of mission that it's that it's meant to. So apart from talking the regular missions where we just measure things, there are multiple other ways where or multiple other missions where the CanSats are used to protect eggs, and also some kind of some CanSats also have a sharp metal kind of structure which is used to see how deep it can dig into ground and things like that. So so once the CanSat is released is when the mission starts, and since then it starts recording. So, and we also have to make sure that the release is, if it's successful or not. And once the CanSat is landed, we can fetch the CanSat and stop the telemetry, and telemetry as in what the information that it's sending. So apart from this, it's equally important for us to be able to receive all the data that the CanSat has sent from the ground station end. So to make things more interesting and fun, we can try and build a good user interface to see all of these in a graphical representation, because it would be more visually appealing, or rather not plain and simple that we generally have. And the obtained data, like I said, so that's something that I just mentioned. Put it into your user interface and makes it more visually appealing. So moving ahead, so we're almost done about how field testing is done. It's crucially important for us to test, to know what our mistakes are and where we can improve based on our test results. So when we have to test every module individually and then put all of them together and test them together as well. So I'll just quickly skim through these. Onboard computer, first we check for network establishment if it's working perfectly fine. When how does this test go on is when once the power is on, the onboard computer has to respond immediately. So once you've stored a code, it could be a blink code or any random code just to check if the onboard computer is working as expected. So we dump the code into the microcontroller and or an Arduino, and once we power it on, it should do as expected, as maybe a blink, a light, or things like that. And if that does not happen, then of course you will have to relook into the design or see where you've gone wrong. And communication module testing is nothing but trying to take the CanSat as far as possible within the allowed range, and to try and transmit some information so that you will be able to receive it at the ground station. So of course, that doesn't happen, then you will have to troubleshoot. And BME sensor, or any kind of sensors for that matter, is something where you put the CanSat out in air and read data from it. And once that is there, we can probably check with some kind of apps or your mobile whether the data that you've been receiving is right or wrong. And if it's right, it's great. Else, like usual, check where you've gone wrong or where the problem is. And GPS module, I haven't spoken about this, but where do we use a GPS module on a CanSat? Let's say we are launching these CanSats to a high altitude for about, let's say, a kilometer. And sometimes when it's windy, these CanSats move really far away because they just drift with the wind and land some at really awkward positions, or or somewhere very far from the launch site itself. So it is necessary at these point of time that one must have a GPS module on the CanSat to recover the CanSat and to locate where it has been. So based on that, I think it's pretty easy to check where the CanSat is and check this particular module itself as to uh, when we get the latitude and longitude, we compare it with where we are currently stationed, and we can compare how it's working. So SD card module, again, this is a very advanced kind of module, I guess. It's not entirely necessary, but it's optional, just to make sure we have good amount of storage on the CanSat. And EPS module most definitely has to be tested. If the electronic power system or the EPS module is not giving enough power to the subsystem, then we're going to have a failure. So we should make sure that at all possible points, or with even with different kind of payloads, that all of them are getting sufficient power. So moving ahead, we are at one of the most important slides of the presentation itself. All this while I spoke about CanSats, their different subsystems, how they're used, why they're used, and all of that. But what's important, or what's very important, is for us to switch from CanSats or progress from CanSats to CubeSats and larger satellites. Like I mentioned in the beginning of the presentation, that CanSats are only something that we start with, and we do not want to be here. We want to progress further in building CubeSats and larger satellites. So of course, we can one must not stick to a particular design and continue forever. There are multiple ways one can improve. So let's say you start building a very basic CanSat, which requires not a lot of effort, which requires very little time, energy, and things like that. So you start there, and one after the other keep adding things and try and challenge yourself to build a better CanSat, or a better reliable CanSat. So once you achieve that, go ahead for tasks which are more difficult, and eventually you should think about a fully functional 1U, 2U, or 3U CubeSat that you can launch to outer space. So that being done, but also about how you can make these really challenging for you, and make it fun for you to experiment and put all your thought into this process, is maybe by having to have access to all this data by a phone instead of an entire ground station. And once, let's say, you started with a particular design and it's taking either too much power or it's taking too much space, then you can work on how to make it even more compact and even more small, and you could have a good user interface. And also, if if you have a bigger ground station, you can not just track your CanSats, but also some weather satellites and things like that. And of course, with the advent of AI and ML, artificial intelligence and machine learning, there is plenty of options, out there for us to experiment and do about how these things can be automated rather than having human intervention. So, of course, I've just listed very few points here, and it all depends to how one wants to think, and how one wants to really take up these CanSat building opportunities to another level. So I think that's pretty much about it. And here I have included some snapshots. So you can see here on the left, it's just nothing but a proto board that we've used some really basic components on it with the batteries and connected with wires. and the second one being a CanSat structure with all these subsystems in place, and about how these ground stations are also set up. So here is a picture of a launch using a drone, and you can see the MATLAB application graphical user interface. So this is how it can look rather than having you know a very plain or a simple screen where we get data. Having a visual representation can really help sometimes. So that's about it. I hope I did a good job. So if you all have any questions, you can ask me.
Okay, Ashbrain, thank you so much for your presentation. I think for me, you did really, really great, and I believe everybody else will actually do so. I just want to check if Jake is here or Jemima, just to take over and check if people have questions. If not, I think we have a few questions in the chat, so I'll just quickly read them.
Yeah, I'm around.
Okay, good. Okay, let me just go on and read them. Okay, so the first question is from Prudence. So Prudence says that without a ground station, we can't control the CanSat. So how easily is it to build one? So I think that's the first question.
So of course, like I said, when you talk about the communication module, it has two parts to it. So if you're able to build one part of it on the CanSat, you will definitely be able to build the other part of it on ground, and it's not difficult at all. The only challenge that I think you will have is to maybe design the antenna. It's not just constricted to electronics. I think you will have to have some knowledge about communications and about how to build an antenna also. So and also to choose the frequency and design your antenna and the gain of the antenna and things like these. But let me tell you, it's not difficult, and definitely it's doable. And also it's really fun for us to get into these things and really design an antenna. So I think it's very easy.
Right. Thank you so much. The next question is from Francis. So Francis says, can we run these softwares on Mac laptops?
Oh yeah, definitely.
Okay, great. So I think a few people also asked if it's possible to get the presentation slide.
Sure. I can share them across to you.
Okay, great. We also have another question from Avishi. I'm hoping I'm pronouncing it properly. So it says, are there any websites from where we can order the equipment required in India?
When you say equipment, if you mean the components like Arduino and the resistors and capacitors and all of these, of course there are websites called as DigiKey or Mouser. This is where you can get all these components from. But if you're asking about CanSat as a whole, the CanSat kit, definitely yes. TSC Technologies, from where I'm a part of, we do hand out kits for the very same reason. And you could get in touch with TSC, people from TSC, and yeah, definitely you could get your hands on these kits.
Okay. So maybe you can put the link to the website you mentioned for the various components to build it into the chat, and people can check. Then the next question is from Guantam. It says, can we talk about custom mechanical design for CanSat chases?
Yes. Maybe that would require some more time
Yeah.
to But definitely that is something that we design in Fusion 360. It's not difficult at all. It's very easy, and just requires us to design something like a tube, and cut down some parts of it to you know meet the weight requirement. So yeah, that's something we can do.
Yeah, I think maybe in the future we could actually have another section on this if possible.
Yes.
The next question is again from Guantam. It says, is there any way to simplify the ground software development?
Simplify, I'm not very sure, but I can, like I said earlier, it's not difficult for us to build a ground station. It's nothing but an Arduino module on the ground station as well. And programming it is also very easy. So nothing much to worry about.
Okay, cool. Kuma also asks, what is the hardest challenge in CanSat design?
Uh, of course, the size, bringing the subsystems that are in a satellite to the size of a Coke can. I think that's the hardest.
Okay. So this is also from Bismarck. He's asking, how will you receive CanSat data in MATLAB software?
So we don't receive the data in MATLAB software. We build a user interface in MATLAB software. So we receive all the data from the ground station itself, or from Arduino and these things. So these values that we get are fed into a MATLAB, user interface, and that's how we are able to see the user interface with MATLAB.
Okay, cool. Again from Guantam is asking, so I don't know if this is the name of a company. It says, are Rocketman parachutes available in India?
I'm not very sure of that.
Okay.
Not really sure of that.
Okay. This is a comment about putting the website in there. Francis is asking, you talked about PCB. Are we meant to print our own custom PCB with a 3D printer?
No, you don't print a PCB with 3D printer. So you design the PCB or the printed circuit boards on the Eagle software or the Fusion 360 software. And of course, there are many more softwares. You could take up designing and design them, and you can give it for manufacturing in any kind of small industry where they make PCBs. So if you are a beginner, I would suggest you to not start off with PCBs. I would suggest go with Arduino boards, assemble these boards, and then think of putting all of these into a PCB.
Okay, great. So another question says, are 2dBi GSM, sorry, antenna possible for 675 meters of height?
I'm guessing it should be.
Yeah. Kuma also asks that which antenna would be better for CanSat with long range up to 700 meters and the compact size to fit a CanSat body?
Well, this is an interesting question. I would say a dipole, because of the compact size. You can fold this into the body itself, and also it gives you a good range. So I think we could do a good job with the dipole.
Okay. So this is from Ransford. Is asking, can we make use of solar panels in our design?
Definitely, definitely. But I don't see any real use for a solar panel or solar cells in a CanSat, because it's not going to outer space. That we could always retrieve it, and also the flight time is for maximum of 2 or 3 minutes, or rather 5 minutes. So I don't see any use for a solar panel, but definitely there is no stopping you from using solar panels. But there is one constraint, which is the size and the weight. You're not supposed to exceed, the size and weight constraint. And of course, you can use whatever you want.
Okay, cool. So I just want to ask Jake, how are we doing with time? Because we have a couple of more questions. Actually, we have a lot of questions. So just check and then let's see if we can continue. So you can send it to me as a message, or you can just tell me now.
I think you can ask a few more questions, then about 2 or 3 more questions, then we move to the second presentation. If at the end of the second presentation, if Ashwin is still around, I think you can answer a few more questions. Else, we'll try and then see how we get the questions answered. But they should keep on asking. I think Ashwin can also answer some questions in the chat while the other presentation is going.
Okay, cool. Yeah. So the next thing is, so I think a few people have asked a lot of questions. So I'm just going to go to other people who have not. So it said, sir, can we get, okay, presentation slide? That's fine. Can we get access? Okay. Okay, so, all right. So if you asked a question and you missed the answer, we recorded this section, so you can always watch and then check. So this is asking which is better to design SMD or PTH PCBs. I'm sure this is an interesting question also that Prof can actually also answer. So yeah, so maybe yeah, ready. Maybe you can answer. Yeah.
Yeah, sure. I mean, in my opinion, it's just about the design and how proficient you are with using SMD components compared to plated through hole. Performance wise, I don't see any difference that that is caused. But if you are well versed with soldering, and if you are able to uh, use SMD, surface mount devices, then definitely I would suggest that, because that is more sophisticated. And of course, when you want to use microcontrollers or any chips, you don't have an option to have plated through hole. You have to have a separate a stack for it, and then embed these microcontrollers to it. So yeah, I think SMD is better.
Okay. So I think this may be the final question. So can weather balloons be used for CanSat testing?
Definitely, yes. Also, weather balloons are used to keep the satellites in air, rather than what we just discussed about launching the CanSats from an altitude. People do use weather balloons to hover the CanSats at an altitude, and test the communication from one point to another, and also communication between different CanSats as well.
Okay. I'll take one more question. Are there any open source firmwares for XB radio modules?
No, sorry, I didn't get your question. What?
So it's asking about radio modules for XB. That's XBEE.
Oh, Zigbee. Oh, yes,
Yes,
yes, yes.
yeah.
Yeah, there are some open source firmwares. I'm sure you will be able to find some things on GitHub and all of those.
Okay, great. So guys, thank you so much. I actually loved the questions that you guys asked, and that really tells that we did enjoy the talk from Ashwin. So thank you so much. Before we continue, I just want us to take a group photo. So if you could turn your camera on, we could do a group photo. And as usual, I don't know how to do this. So just turn your camera on if you can, and we can take a group photo and then just move on to
Just a moment.
yeah. So if you know how to do it, just I've put down the grid, but I don't know how to. Well, I can take a screenshot, I guess.
Yeah, hold on.
Okay.
Yeah, using.
Okay. Okay, so can somebody take the screenshot? Oh, okay, I figured it out. I just had to drag my screen and here. Okay, cool. Okay, right. So smile. Okay, thank you. Great. I think I needed to Canada. So just a minute.
There are other colleagues from the other side, so
This
try
side, yeah.
well.
Yes. So I have taken this one. Let me take another one. Just a minute. Maximize. Oh, where are we again? Yes. So I just have to. I'm sorry, I'm not used to this.
No problem.
Go down. Yeah, go to the other side. Yes. So a lot more people here. So please.
You
Oh.
can always press Alt plus print screen.
Eric, maybe you can do it from your end as well, right?
Yeah, I've done it. I've already posted. Yeah.
Awesome.
Okay, great. All right. I also have a few more here. Okay. All right. So thank you. I think that should be it. Let me see. There's another page. Oh, there's another page. Okay. All right, but that should be it. Yeah. Thank you, guys.
Awesome. Yeah, I was really glad to do this. We'll do this more often.
Yeah, we should. We would definitely do this more often.
Yeah,
All right.
we all learn great stuff from you.
Yeah, likewise.
Ready. I think maybe you can give. I will take your contact from Solo and maybe contact you for some few stuff. Okay.
Sure, definitely.
Yeah.
Okay. So Ashwin, please, you can put the link about where you can get the various parts to build a CanSat if you are in India to do so. And so you can put that in the chat.
Sure.
Move on.
I'll yes.
Right. Okay. So I just want to say that thank you guys so much, especially people joining from India. I know it's late. It's actually 12 midnight past there and people are still here, which shows the commitment. So thank you guys so much. And yeah, I'm hoping you enjoy the rest of the section. So I'll stop talking now.
Okay. Thank you very much, Solomon, for moderating the questions. Thank you very much, Mr. Reddy. Your presentation was very thorough and very informative, and we understood everything. And from this, I've learned a few things, and I'm sure everybody else has learned something as well. Now, with time almost fast spent, let us introduce our next speaker. And our next speaker, he is a man passionate about education, science, and technology. And he's a physicist, programmer, full stack developer, teacher, and electronic hobbyist. His passion in teaching and learning enabled him to create this corporation, Electronics. And they deal in software design, website design, embedded system, teaching assistance, programming tutorials, and the whole lot. And now with a warm welcome, I would like to introduce Mr. Eric Obeng, aka Professor. Professor, the ball is your court.
All right. Thank you very much for that lengthy. I don't know whether some of them are true, but I'll take it.
Oh, okay.
All right. Good evening, everyone. I trust we are doing well. Hello.
Yes, we are doing very well.
Yes. Yeah, we are.
Okay, so allow me to share my screen quickly. Thank you. All right. Ready. Thank you very much. I think that there was a point in your lecture that I really enjoyed. It's something that syncs with my lecture. So I was like, wow, that's good. That's great. Okay, so previously we had met for Electronics 101. Today we are going to look at Arduino and some fundamentals that you need to know in order to have enough confidence not to build your burn your Arduino board. In fact, my duty today is to prevent you from ruining your Arduino board because it costs a lot of money. So I'll be presenting today, I'll be talking about Arduino hardware. And of course, I'm Mr. Kobeneke Professor. You can always link up to me on my personal website. Okay, so these are, for the sake of those who don't know about me, these are some of the products or hobbies projects that I've done some past ago. Of course, this were time of fun. Right now, we do it for the cash, not for the fun. Okay, so let's get started. I want us to look at a little bit of biology, and I don't want you to get scared. I want to draw an analogy which would help you understand what I'm about to do very well. So let's look at a little bit of biology. In biology, we know what a cell is. We've learned that is the basic unit of life. Now, when you put similar cells together to perform a particular function, we get a tissue. You put different tissues together performing the same function, we have an organ. And then when we put different organs together, we get what we call a system or an organ system. And a typical example of the organ systems would be digestive, excretory system, nervous system. Now let's take a look at the nervous system. I just don't want you to be nervous, okay? All right, so on this slide, you can see that this doctor, I don't know what he's checking at the knee, but the guy reacts quickly and then the doctor actually enjoys the reaction. But what I want to show you here is on the left. You can see that when as the knee is stimulated, there is this signal that travels through the blue line, which represents the neuron. Then it makes a quick arc in what we call the relay something. You can consult your biologist for more information. And then a muscle is affected or instructed to take an action, okay? Now I need you to hold on to this thought for me. Now, if you take every normal human being, everybody, so far as you're a human being, chances are that you have 5 senses, okay? We have the sense of touch, smell, and all those stuff. Now, a few people, including myself and maybe Solo, we have a 6th sense, which is the sense of humor. So if you're able to decode this particular one, then it means that you haven't lost your sense of humor. Okay. Now, what's the importance of our sense organs? First of all, it's a way, they serve as the interface to our brain. And when I talk about interface, take it as your computer, okay? Everything going on, all the amazing things going on inside the computer, you're able to see through the screen, you're able to interact with the computer through your mouse, through your keyboard. So you don't have to open the computer's motherboard and be touching things for it to work. Through keys and commands, you're able to work with it. So the mouse, the keyboard, and the monitor serves as the computer's interface. So the same way our sense organs are serving as interface to our brain. And with that, they help us to interface with our environment. So as humans, when we go to a place and the weather is very warm, we want to offload some shirt. If it is cold, we want to put on some shirt. Depending on what our senses are giving back to us, we react, okay? So you are making your food, you taste it and realize that the salt content is low, you react, you act on that information. So our senses help us to interface with our environment. And lastly, they also help to provide our brains with data to make decisions. So whether you are to run or to fly or whatever, it's all based on whatever your senses are picking. So if you hear a lion roar, this information helps your brain to decide, my friend, run for your life. And you do run for your life, okay? Now, so a typical nervous activity will be something like this. So let's say we have a stimulus on your skin. Now that stimulus is actually converted to an electrical signal by your receptors, okay? So there are these sensory organs like your skin, they have something called receptors that converts the physical stimulus into an electrical one, which travels through your neuron. Please, signals don't travel through your blood, okay? They travel through your neurons in the form of electrical pulses. And in this particular situation, they don't go to your brain first. They go to what we call the motor relay, which is in your spinal cord. And then your spinal, immediately there is a response which makes your leg jerk. Now, there are other things that would have to go through your brain for your brain to make a decision and then effects an action, okay? All right. Now, this particular scenario is a protective mechanism of the human body so that you don't hurt yourself so much when something bad is happening to you. Okay. Now, in engineering, there is something called biomimetics or biomimicry, which is a way we emulate natural phenomenon to solve problems. And it's something that I have embraced. It helps me so much when I'm trying to model things that seems quite complex, because nature always assumes minimum energy. So usually when things exist in nature, they are usually stable, right? So if you find means of emulating how nature does it, it's always the best result. So for instance, from a pigeon's flight, an airplane was invented. From a dragonfly, we have a helicopter and all those kind of things. Okay. All right. Now, put everything we've seen about the biology analogy here in your mind, because I'll be relating to it very soon. Now, let's look at embedded systems. When Reddy was talking, you realized that there was an onboard controller, there was a payload, okay, and the onboard controller, he said, is the brain of the CanSat, okay? Fantastic. So a system in generic definition is a group of units working together according to a set of rules. Now, when we say that something is embedded, it means that one thing has been fixed into another. So when we put this together, we can define an embedded system as a system which has a dedicated function in a bigger or a much larger system. So if you look at a typical embedded system structure, we have sensors, we have ADCs, which stands for analog to digital converters. So like your sensory receptors, which converts maybe the touch to electrical pulses here. Your sensors are serving as your sensory, your skin or your eye, your sense organs. And the sensory receptors are serving as the ADCs, which converts the electrical pulses coming from the sensors here into digitized form that the computer or the microcontroller that you are using can process. Then through that, the microcontroller makes a decision, calls a certain actuator. An actuator here is a transducer. It's a form of a transducer, but usually in the form of a mechanic, something that converts electrical energy into a mechanical form. So that could be like a relay, a motor drive or something. So maybe you are trying to sense, this is a system controlling your outside light. So you have a light sensor here, which gives you analog voltage. Then you have something converting the analog voltage into a digital voltage, which passes that information to your microcontroller. Microcontroller now causes maybe your switch, a relay controlling that light to turn on, okay? So this is just a basic model or a typical model for an embedded system, which is something that we seek to build. Now, putting the nervous system and embedded system together, realize that there is a lot that we can learn from our own self when we are building the systems that we are about to learn how to, okay? So in terms of our five senses, human beings, yes, we have just the five senses, except the few of us who have the sixth one. But for electronics, we have so many of them. We have ultrasound, we have gas sensors, PIRs. Depending on the application, you choose the appropriate sensor for your work. And all you have to do is to know how to interface it with your microcontroller for your things to work. So for nervous systems has the sense organs, embedded systems has the electronic sensors. Now, in the nervous system, signals will travel through neurons, but in our embedded systems, we will be using wires or PCB traces, even sometimes wireless communication protocols, okay? anything to get our message or information delivered. That's what we are looking at. Okay, then in terms of effector muscles, like your biceps or your triceps, in embedded systems, you'll be dealing with things like relay switches, actuators, or whatever action needs to be done when a particular condition is met. Is basically what we are referring to as an actuator, okay? Then the brain here, like Reddy said in his presentation, is our microcontroller. And the typical one that we're going to learn today is the Arduino Uno. Any questions up to this point? Okay, so let's continue. So the Arduino platform, the hardware, let's look at it. When we talk of a platform, in computing terms, we are referring to a hardware and a software unit, okay? But then there is also what we call the software-only platform, and a typical example is the Java Virtual Machine, JVM, what makes it possible to run Java applications on your machines, okay? So if you take something like the PC is a platform that's made of Windows operating system, and originally the HP whatever. Then we have the Macintosh, which is the Mac hardware and their OS. If you look today, we usually are referring to Android phones, iPhones. So all these represent systems because it's an embodiment of a hardware and a software unit. Now, if you take Arduino, Arduino is also a platform because it comes with its own physical device, which we will be looking at, and also a set of software components that help us to program it, okay? And the word Arduino actually could mean three different things. The first one is the company itself, okay? Or it could also mean the Arduino as the physical board, or it could mean Arduino as the software. So the meaning of Arduino tends to be contextual, as in depending on what is being taught or the context of the discussion, you derive the meaning. Now, one thing about Arduino is that it is an open source platform. When we say that a platform is open source, it means that the source code, the very makeup of that particular thing is available for anyone who is interested in improving on it or editing it for whatever purpose that they want to use for. And it has become one of the most popular, in fact, if I'm not going to say the most popular project board for thinkers and then beginners, okay? And if you look at Arduino itself, it's made up of the programming language and which is based on a program called wiring. Those who are curious, you can look up on wiring. Okay, so they actually built Arduino, the Arduino programming language on top of a programming language called wiring, or a unit called wiring. And the Arduino software, that is the IDE, is based on another program called processing. If you've used processing before, you would identify with what I'm talking about. Now, why do we want to use Arduino? Okay, so relatively in terms of cost, it is quite cheaper. Okay, but that of course depends on your pocket. But compared to other microcontroller systems that you would want to use, Arduino is quite cheaper. And one thing is cross-platform. Cross-platform here means that you can actually use Arduino on any of the major OS, talk of Windows, Linux, and Mac OS, okay? Arduino you can install the Arduino software, sorry, on any of them and use your Arduino board, unlike some other microcontroller boards that are Windows only. If you look at the programming language, you realize that it's relatively simpler. And like I said, it is open source, and the software is open source. The hardware itself is also open source. And there is a very big community that can help you when you get into trouble. It can help you to come up with a solution. Now, whenever you are doing a project, one of the challenges is how to select the appropriate Arduino board, because there are a lot of Arduino microcontroller boards, different ones. So one of the things, the first thing is which Arduino board would be suitable for my project. So I want us to look at the various Arduino families that we have. We have what we call the Maker family. The Maker family is purposely designed for cloud and IoT, that is Internet of Things applications. Okay, so if you want to use an Arduino product in an IoT project, then you should look at the MKR family, because they are actually those that are geared towards IoT and cloud connectivity. Now, at every point in time, there are certain terminologies that could confuse you. For instance, boards and a shield or a module, okay? The Arduino boards, for instance, if you take the Uno, that's the board, or the Mega, that's the board. A shield is an external peripheral that you can attach to your board for it to extend its functionality. For instance, a typical Arduino Uno is not capable of Wi-Fi communication, right? So if I'm building an application and I need Wi-Fi communication, I can buy a Zigbee or XB, whatever you want to call it, shield, and attach it to it, which now gives Arduino the ability to communicate via the Zigbee protocol. Okay, so those are usually called shields. Okay. All right, so we have the MKR family. Then we have the classic Arduino family, where we have the Leonardo, the Arduino Mega, Micro, Uno, as we all know. Then we also have the Pro family. The Arduino Pro is specifically designed for industrial applications. So typical examples are the Potentas, okay? So we have Potenta 87, the 87 Lite. These are industrial grade, because when you are doing things for the industry, there are certain standards that you need to follow, and these Potentas have been designed to meet exactly that. Then finally, we have the nuclear family. That one doesn't have a lot of boards. I think the only one I have seen so far is the Sense ME, okay? And there are a lot of Arduino boards that have been retired. In fact, Arduino Ethernet, Arduino, whatever, Duominolo, most of them have been retired, but you will still get their source codes online in a way. So in case you are curious, you can follow this link for that. Okay, so in this particular training, we are focusing on the Uno. So I'm going to narrow everything down to the Uno. If you take the Arduino Uno board, okay, now I need you to take note of this. It is easy, or we lightly or loosely call the Arduino board the Arduino microcontroller. Yes, in a very non-technical sense, that is not wrong, right? But actually, the Arduino itself is a microcontroller board. Take it as the circuitry that has been built around the microcontroller itself. Now, if you take an Arduino Uno board, it uses a microcontroller called the Atmega 328, and that is what I'm showing here. So this is the computer itself. This is the actual microcontroller. What we have here, which is the green thing, is the Arduino Uno board. Okay, so there is a difference between the board and the microcontroller itself. Okay. All right. Now, if you take a typical Arduino Uno board, there are actually two microcontrollers if you have the original Arduino. But if you have the clones, like those that we usually get from China, they usually have just one microcontroller. And you get to know why they have one, but the original has two. Okay, so if you take a typical Arduino, the Atmega 328 ICs come in different forms. In fact, I think I know of 3 different forms. We have the DIP, we have the SMD, okay? But there is another smaller version, quite smaller than this one, okay? That package is also there. At least I know of these 3 packages, okay? And for beginners, usually we want the ones with this big IC because it is easy to throw it away and replace it in case it gets spoiled, okay? Most of the time when you develop faults, it's not from the board, sometimes it's the microcontroller itself, or maybe sometimes some fuses that have blown. But once you replace them, you usually get your boards working. So mostly for newbies, we want this one compared to the SMD ones, because the SMD requires some level of technicality to work well. Okay, so if you take the Arduino Uno, the processor, the main processor, which is the Atmega 328, it has some interesting features which actually also defines the features of the Arduino Uno. The first one is it uses a type of processor called the AVR, okay, and it can run from about 16 megahertz. Sorry. It can run from about 16 megahertz to 20 megahertz. Yeah, you can put a clock, a crystal oscillator of this frequency on it. Now, it has a 32 kilobyte flash. The flash, take the flash as your hard drive, okay? That is the place where you upload your sketch or the code that you've written. Okay, that's where you upload the code. Now, the memory, which in our usual computers we call RAM, okay? In here we call it the static RAM. Arduino has just 2 kilobytes of it. So you see, if you are a regular desktop programmer and you are not very cautious about variable declarations and memory management, trust me, your life on Arduino is not going to be an interesting one, because here you are resource constrained. So everything that you are doing, you should make sure you need it before you put it in there. Then we have what we call the electronically erasable programmable read-only memory, EEPROM. This particular storage is a very interesting one. Sometimes when you build applications, you want to save some configurations like user settings, okay, things that are not supposed to be loaded in memory but should persist so far as the application is running, okay? Usually you want to save those things on the EEPROM, but maybe I will get the time to talk more about the EEPROM, some of the things you don't do with it. Okay, so these are the 3 basic memories that you can have on Arduino: the 32 kilobytes flash, which is like your hard drive, the 2 kilobyte SRAM, which is like your memory, and the 1 kilobyte, which is an EEPROM, something that gives you a permanent storage. Now, Arduino has some security features, and there are 2 of them actually. We have what we call the power on reset. If you've used an Arduino board before, you realize that anytime you connect power to it, it resets, okay? That is a feature that is actually built into the microprocessor or the microcontroller, okay, which makes it reset. So the moment it gets power, it resets to start the executing whatever application you've loaded on it. The other thing is what we call the brownout detection.
Prof, so
yeah,
can you check your camera? You can only see part of your head.
Really? Okay. I'm not seeing my view in a way I would want to. Let me see. The view. Okay. Is the camera okay?
Yes, it's fine now.
Yes, please, it is.
Okay, fantastic. So the brownout detection is a feature built in the processor or the microcontroller that makes it able to detect that the voltage it's working with has dropped, or there is a dip in the voltage. Okay, so that's the brownout detection. Then there are other peripherals that make certain features possible, like the timers and the USAT. USAT stands for Universal Synchronous Asynchronous Receiver Transmitter, which is a communication protocol that makes it possible to connect your Arduino to other devices and program them using the TX and RX pins, okay? We'll talk more about those things later. Okay, now continuing, we also have communication protocols. I've talked about the USAT. We also have what we call the SPI. We have the I2C. We'll get time to talk about these things, but this is just an overview, so I'm not going to waste time on it. Then there is an analog comparator, which makes it possible for what we call the, how should I even put it? Okay, we will be taking data like from microphones, from light sensors, from and all those things. Okay, so those data comes in the form of analog signals. We have to convert them one way or the other, and that is where the analog comparator comes in. Then there are those who are much advanced, you know, of what we call the watchdog timers and the PWM pins. I will talk about these things in later sessions. Now, the ATmega System U is not something available for you, the user, okay? Yes, it is another microcontroller that you can use separately for your work, but not on the Arduino. On the Arduino, it's serving as a co-processor, which makes it possible to interface your Arduino with your computer. Is that okay? So anytime you connect your Arduino to your computer, what makes it possible to load code or transfer data between your computer and Arduino is this ATmega System U. But of course, this is only available on the, sorry, on the original Arduino boards, okay? For those Chinese clones, they usually come with other programmers like the CH340, FTDI, and all this stuff, okay? All right, and a typical Arduino, the microprocessor can be powered, not the Arduino, please. The microprocessor on it, which is the ATmega, can be powered from 2.7 to 5.5 volts, okay? All right, now the recommended operating conditions. This is a very important thing to know. If you've bent your Arduino before, then chances are that you connected a voltage that is not recommended for the Arduino. Okay, so take this from me. This is a very important information. So if you don't know it yet, then take note of it. The minimum voltage you can supply. If you look at a typical Arduino, there is a pin labeled V-in, or there is this DC barrel, something, the place that you can insert external voltage, okay? The minimum voltage should be 6 volts, and your maximum, according to the specification, should be 20 volts, okay? But then later, I'm going to show you why you wouldn't want to use something like 20 volts for your applications, okay? I will show you that. Now, if you are powering your Arduino from the USB cable, then the maximum you can handle should be 5.5 volts. In fact, that is the maximum of the processor. When you power your Arduino with the USB, you are connected directly to the ATmega. Okay, so any spike will damage your ATmega. If your fuse doesn't get defend your ATmega, any little spike can destroy your processor. Okay, so but fortunately, the USB is coming from the PC, and most good PCs have very stable voltage output. Now, the recommended or the nominal current that each Arduino pins, and we'll be looking at Arduino pins very soon, can source is 20 milliamp. This is to say that whenever you are connecting something to the Arduino pin to switch it on, make sure that that thing can take a maximum of 20 milliamp. If you connect something that requires, let's say, 50 milliamps to your Arduino pin, it's not going to work because the Arduino pin can only deliver a maximum of 20 milliamps of current. So you should get these things done. Now, when it comes to how much power the Arduino consumes, it's usually dependent on the application, how many pins you've connected, the external devices that you've connected to Arduino and all that. Okay. Now, if you look at the technical specification, this is the outline or a diagram showing how the Arduino is powered. So we have the V-in and USB, okay? But the V-in goes through a linear voltage regulator, which steps it down to 5 volts. So whatever voltage, I remember the recommended is from 6 to 20, is stepped down to 5 volts. And for the USB, it is directly 5 volts. But then there is this op-amp, which is serving as a comparator. What the op-amp does is, if it detects that there is voltage coming from the V-in, then it switches and gets make the Arduino takes power from your V-in, not from your USB, okay? It only depends on the USB if there is no voltage coming from your V-in. And that, is, I think, is a very beautiful feature they designed in there. Now, these are the maximum currents that these various aspects of the Arduino can take. So the ATmega System U2 can take a maximum of 261 milliamps of current. The Mega 328 can take a maximum of 410. And then the green LEDs and yellow LEDs also have this voltage drops. This current maximums. And every Arduino Uno board has a 3-volt output, which you can use as a means of delivering voltage to CMOS devices. By CMOS devices, I mean devices that depends on 3 volts levels, okay? So remember, you cannot power the Arduino through this 3.3 volts pin. You can only source power from it, okay? So if you take a typical Arduino, these are the pinouts, and I'm going to step through each pin and talk about what you do with the pins, their specifications and all that. So I will leave this here. You can reference it later. So the first pin on it, there is no label. If you have an Arduino with you, you can take it and check it. There is no label on that first pin. It's actually left for future compatibility of the product. It doesn't do anything, okay? But they left it just in case something else. But the next pin after that is the IO ref, which serves as the DC reference voltage for the Arduino digital pins, okay? We'll look at the digital pins later, but at every point in time, this pin here is serving as the reference voltages for your input and output pins. And usually if you connect a voltmeter, they read 5 volt because the Arduino operates at a 5 volt TTL logic. Okay. Then next we have the reset pin. The reset pin is used for resetting the Arduino. It is actually linked with this reset button, okay? So if you press this reset button, it resets the Arduino. Now, resetting the Arduino doesn't wipe the data on it. It merely causes the Arduino to restart its execution. It doesn't clear the data you've uploaded onto it. It doesn't wipe. It's just saying, hey, restart your program. Is that okay? That is all that the reset button does. But you see, if you actually have access to this button, then yes, you can press it. But in typical applications, when you embed this Arduino, you won't get the chance of coming to press this reset pin, reset button. So it's broken out here so that you can interface your own button or whatever means of resetting to it and use it to reset Arduino just like you press this button, okay? Then we have the 3.3 volt output, which I said is only used for supplying 3.3 volt power. It is not used, or you cannot use it to power your Arduino, okay? Now, after this 3.3 volts, we have the 5 volts power. Now, the 5 volt is bidirectional. That means it can source or sink. You can use it as a means of powering up your Arduino, or use it as a means of using the Arduino to power up other devices. Sorry. Okay. Now, this is possible because this particular onboard is connected to this item here. I don't know if you can see my cursor moving. That is the 5 volt regulator, okay? So its output is fed directly to this guy, okay? So if you choose to build your 5 volt, or let's say you have a constant and a trustworthy 5 volt supply, you can connect it to this 5 volt as a means of powering up your Arduino so that the Arduino does not have to depend on this onboard regulator, okay? But if you don't have any external 5 volt supply, then you can actually use the DC barrel or the V-in pin, which will go through the onboard 5 volt to get your microcontroller the needed 5 volt supply. And again, you can also power your Arduino using the USB connector. Then we have the ground pin, which of course is the point of convergence for all the voltages. Ground, which in most times we reference as 0 volts, okay? All right. Then we have the V-in pin, which I've spoken about, that per technical specifications for between 6 to 18 or 6 to 20 volt. But like I said, this is a linear voltage regulator. So that means that the higher your input and the lower your output, the lower the efficiency. So if you put something like an 18 volt V-in, you realize that this side of your board is heating up. and you can actually compute that by calculation, okay? Even when you power your Arduino with 7 volts, you realize that this guy here will only operate at about 70 something efficient, okay? But the higher your input voltage, the lower the efficiency. That means it will be dissipating a lot of the energy as heat, and your Arduino board is what is going to take the heating. So something I will recommend that you should not do. Okay. Now, beneath the power pins, we have the analog pins. Now, take note. The analog pins are for input only, analog input only. You cannot use them for analog output, okay? You can only use them for analog input operations. That means if you have any analog data, you can use it to read, or it has an ADC, which is an analog to digital converter that can convert that analog data into a digital form that the Arduino or the microprocessor can handle, okay? But you cannot use it as a means of generating analog output. However, you can actually configure these analog pins to serve as digital pins. And when you are using them as digital pins, they have the labels 14 through 19. So this becomes pin 14 because the last digital pin is 13. So this becomes 14, 15, 16, 17, 18, 19. Is that okay? So that means in total, there are about 20 digital pins or GPIOs, right? But if you are using them as analog input, then you cannot use them for digital operations too. So you have to choose one of them. At any point in time, you can either use it for analog input or for digital operation, but not both at the same time. Okay. Now, analog pin 4 and 5 also have special functions, which we call the twin wire communication or I2C communication. I'll talk about this later. But in I2C communication, there are two specific signals called SDA and SCL, serial data and serial clock. Pin A4, analog pin A4 becomes your SDA, and analog pin A5 becomes your SCL. So those of you who have used something like real-time clock and RTC, realize that RTCs are usually interfaced with Arduino using I2C, and you use this SDA and SCL lines respectively. So usually this is where you connect those things. All right, now from the analog side, let's move to the digital realm. The digital realm is where we get to do our binary operation, 0 or 1, on or off, okay? Now, there are 14 digital pins labeled 0 through 13. Is that okay? Now, one thing that I always say is that make sure if you ever intend to use your USB for communication, then don't ever touch your TX and RX lines, okay? If you use them in your circuit to connect to any other thing, chances are that when you want to upload program, you would have to detach your Arduino board from the circuit, load your program, and connect it back. And trust me, that is not something you want to do. So usually in all the applications that I've designed, I never use the RX and TX lines unless I'm using them for UART communication, okay? Now, with that said, if you look at these pins, you can see that some of them has this tilde sign. The tilde sign is what looks like the logarithmic sign, okay? It looks like the logarithmic sign. These pins, the tilde sign just tells you that these pins are possible for able to do what we call pulse width modulation, which I may talk about in later sections or probably tomorrow. But in all, these analog pins, you can use them for outputting switching operations. You switch on or low or high or on, okay, something like that, okay? All right, so we talk much more about the PWM when there is a need, but for now, know that you have 13 digital pins by default. And I'm saying that stay away from TX and RX, which is pins 1 and 0, because they are internally connected to your USB, and once you use them, it makes communications some way. But then, in case there is a need for more digital pins and you are not using your analog pins, you can actually configure them to work as digital pins. Okay. Great. Now, each of the digital pins has something called a pull-up resistor. Maybe tomorrow when we look at some of the ways we can interface external circuits to the pins, I'll show you what a pull-up and a pull-down resistors are. But for now, just keep it in your head that there is something called a pull-up resistor, and I'm going to explain to you tomorrow, okay? And this actually is, you can switch it on or off, so you can activate it using code, okay? So we will come to that. I'll talk more about it, its use, and some of the applications for those pull up and pull. Okay, now, according to the specification, technically a pin can supply 40 milliamps, but then please stay away from this, okay? Just don't do this. When you do this, you put so much stress on your pin, and that register controlling it can actually get one, because pulling this amount of current through that pin can warm it so much, okay, and you can have issues with. So just stay away from this. Look, use the nominal 20 milliamps max, but even that, try as much as possible not to be pulling that much current from Arduino pin. And tomorrow, I'm going to show you some of the ways you can, some of the things you can do in order not to draw so much current from your Arduino pins. But today, it's all about the overview. Okay. So I already talked about pin 0 and 1. Please, when my time is up, notify me. I think just 5 minutes, let me be running up. We shall continue tomorrow. Pins 2 and 3, there is something called interrupt. For instance, as I'm speaking right now, if Solo tries to draw my attention to something, we will say that he has interrupted my speech, right? So I will pause, attend to him, and then after, continue from where I ended. Okay, that's an interrupt. There are times that your Arduino is doing some execution, but you want it to attend to something quickly. Maybe some sensor has triggered, you need Arduino to process that data before it continues with its normal operation. We use a technique called interrupt, and you can only use for the UNO. Pins 2 and 3 are the only pins that we can use for the interrupt. We shall look at how to use the interrupt, God willing, tomorrow, okay? And like I said, all the pins with the tilde sign on them are used for PWM, which is something I'll also talk about in details, God willing, tomorrow. Okay, we only have 4 minutes for today's section, so I think I'm going to end here. I'll continue this slide tomorrow. You don't want to miss the rest of the lecture. All right, any questions?
Great, Prof. Thank you so much. I think we have a few questions, so let me go through it. So Raymond says that, hello, Prof. What is the difference between the ATM Mega 328 and then the same thing but a P with it?
Okay, so one of them, the P stands for pico power. Okay, you can read more about it in the ATmega, but the P stands for pico power, as in it depends on very, very little amount of power to work. Okay, that's what the P stands for. But actually, there are other things. We have AU, P, even the P's, we have PAU or something like that. They are all just variants. Okay, sometimes it's just the package shape. You see, I showed you one that has the DIP, and I said there was another one, the SMD, and I even said there is another one which is much smaller than the SMD. So usually these things have another character defining the kind of package. But for the P, it stands for pico power. That is what I think, yeah, if my memory serves me right, that's what it stands for, and it means that it can actually work on very low energy. Yeah.
Okay, thank you. So there's another question from Avishi. So it reads, could you explain interrupt again?
Okay, so interrupt, physically, like I said, I'm teaching, then maybe I have a phone call, so I attend to the phone call. After the call, I come back and continue with my teaching, okay? That is in physical life what an interrupt is. So in the Arduino world, sometimes maybe you have the Arduino is executing some routines, okay? It's performing some function, but then you want it to always attend to a certain sensor reading. Maybe that could be a doorbell alarm, right? So anytime somebody presses the doorbell, you want to immediately attend to the doorbell. Or let's say you have deployed a CanSat and any sign of signal lost or connection lost, you want something to happen. This is something that needs urgency. Okay, so these are some of the things that in your application you want to give priority to, right? So anytime you want to give priority to something, as in you want the Arduino to suspend whatever it is doing and attend to that thing, you interrupt that the Arduino, and you can do that using the pins 2 and 3. But tomorrow, God willing, we will look at how to do this physically. Okay, so I don't know if that's okay for you now.
Okay. I mean, for me, yeah, it's clear. Yeah, Avicii also says, yeah, got it. All right.
Okay.
So if you do have any questions, I think because we kind of started late, we actually have 4 minutes to go. So if you have any questions to ask, please go ahead and do so. If there are no more questions, then I'll just ask Jemima and Jake to just summarize and finish off today's section. All right, so there's a question from Gupta. It says, I want to connect Arduino Nano with Pixhawk flight controller and send the sensor data via telemetry to ground control. How can I do that?
Okay, that's an interesting one. Okay, so that Pixhawk flight control, I don't know what it is, but I'm assuming it's some module, right? Now, technically, these modules would expose an interface, a means of connecting to it. Sometimes it can be a communication protocol like SPI, I2C, or UART. Okay, so far as any of these communication protocols or interfaces are available, you can hook it up to the Nano. The Nano is actually a variant of it also uses the Atmega 328, which also has the SPI, I2C, and UART. So once any of these communication protocols are possible, all you have to do is to hook it to your flight controller. But then Nano alone, since you need to send your data back to the ground, that means you need some form of wireless communication. Okay, so that means there will have to be something else giving you a wireless communication functionality, something like a LoRa or maybe a GSM module, whatever thing that is possible. Okay, yeah, so basically it's Nano connected interface with your flight controller. Then the Nano will now read the data from the flight controller and transfer it via whatever communication interface you have with it. Then the ground-based connect device will also pick the data up for login or for presentation.
Okay, thank you so much, Prof. Do we have any more questions? Yeah. Okay, so this is from Raymond. So it says sometimes when designing your device, you would like to go with the microcontroller alone without the Arduino board. Any advice on how best to do that?
Okay, so one thing that you should know is that the Arduino is for tinkering, is for hobbyists, okay? Technically, you should not insert Arduino in your final user deliverable product, okay? The Arduino should be like a quick way of prototyping, testing your ideas, okay? But just imagine if you are building, let's say, a PIR controlled light, then you put a whole Arduino board in it. It just makes it unnecessarily expensive. You get the point. But then the Atmegas themselves, at least you can get them for a couple of bucks in China, which is quite cheaper. And for me, I can tinker with the Arduino board, all right, but all my final product, I don't put in an Arduino. I use the microcontroller directly. So if you have the technical expertise to do that, yeah, then that's always the best. So you can always reserve your Arduino for tinkering. Okay, that's what Arduino is supposed to be, for prototyping, not for a final product. But yes, of course, people do put them in final product, but that is not what they're supposed to be used for.
All right. Thank you so much. Do we have any more questions? Yeah, I think I can give 1 minute and then yeah, we should finish in the next 5 minutes. So Jemima, maybe you guys can get ready and then yeah, I think we don't have any more questions. So I would say that thank you guys so much for joining. We just have a few announcements for tomorrow. And then yeah, we can end the section. So Jemima, take over.
All right. Thank you very much, Solomon, for answering the questions. Sorry, for answering the questions very briefly. Also, thank you, Professor, for a wonderful presentation. Helped me to understand the hardware of the Arduino board. In fact, I was watching a few YouTube videos and I don't think did a good job like the way you did. Thank you, Professor. You've really done the topic very well. Now for the announcements. Tomorrow we are meeting here at the same time, 6 p.m. GMT. I think those in India is 11. And we are sorry about the time. However, we don't know what we can do about it. But thank you so much, all our friends from India. It's really been a pleasure having you with us and seeing you faces. We are very excited and we are very happy that you are here. And I hope you had a lovely time. And the poll, for those who haven't filled the poll, let me give a few, let's say 1 minute for you to fill it just now so that we will know how best we can do things well around here. Yes. So if there is nothing else to be said by my fellow partners, I think we will call it a day.
Yeah. So
All
yeah.
right,
So
thank you, Jemima. I think we also like to acknowledge our sponsors, and I want to say a big thank you to Xavier Space Solutions.
Yes, exactly.
To
All right.
Academic City, to Electronics, with Professor. Thank you very much for your presentation. And Space Generation Advisory Council, World CanSat and Rocketry Championship. Thank you, Ashwin.
Yeah.
Thank you, Moonmart, Astronautics Academy and Research Science, and to all our other partners. We want to say a big thank you to also the participants of the GCRC, to all participants of this particular event. Yes, and we would want to see you here tomorrow. Professor will continue with the course on the Arduino. And if you have any questions tomorrow, you can come and ask. I think Ashwin will also be around to answer a few questions, and then we continue with this session. So on that note, would like to end today's meeting and see you tomorrow. Sorry, see you tomorrow.
Yeah.
And bye, everybody.
Everybody, goodbye. Thank you very much.
Have
I'll
a
see you
good night.
tomorrow. Okay,
so
good
whilst
night.
we are saying goodbye, so I'll say that I'm going to send the link to today's video together with the slides if I have it before tomorrow's section. So be on the lookout for that, and also links to our YouTube pages among others. So thank you guys and see you tomorrow.
Yes, please.
All right, bye, everybody.
Bye. Bye, everyone.
So bye bye.
Bye.